We're now going to take a look at some of the integrals that we use in fluid mechanics, and we'll begin with the line integral. And so what we'll do, we'll begin by defining some arbitrary vector field A, and we'll also define a curve, and the curve is where we're going to be doing the line integral on. So we'll call this curve C, and we'll say the curve is going in space from A to B. And along that curve, we will have some differential element ds. And there will be a vector in the direction of ds. I'll put a unit vector n. And over this differential element, let's assume that the vector, our vector field A, is this. So it has some value over that small differential element. And let's write ds in terms of a vector. So ds written in vector form would then be the scalar value multiplied by the unit vector that we set in the direction n. So let's assume that we're wanting to evaluate the line integral from A to B along curve C. And so if we're evaluating this, what I'm going to do in the integral, I'm going to put a C showing that we're integrating along a curve, and we're going from A to B, and we would have our vector A, and the way that we do this is we use our dot product. That would give us the vector component along the direction ds, and that is the way that we evaluate a line integral. Now it turns out sometimes in fluid mechanics you'll want to evaluate one of these line integrals with a closed curve. So where the curve closes upon itself, and you might do that, for example, if you're looking at quantifying the circulation about an airfoil. You can measure the velocity in the velocity field integrated along a closed curve. That would tell you the bound circulation on that particular airfoil. But if C is closed, so we might have a curve that looks like this. And then I'm going to draw the differential element here, ds, and that is a vector. And again, we have our vector A. So if the curve is closed, the way that we do this in fluid mechanics is we will close the sign in the integral. It's no longer a C, and we'll put a little arrow on that, and that arrow would indicate the direction with which going around the curve is being viewed as being positive. So that is an integral around a curve. And again, to evaluate it is just the dot product of our vector field that we're interested in and ds. And so by convention, quite often in fluid mechanics, what we will do is we say counterclockwise is positive. And if you have a hard time remembering that, imagine yourself walking around the curve. So here you are, you're walking along. Imagine that you're walking in the area that you're integrating around is always to your left. And so that's an easy way to remember, or just remember counterclockwise is positive. Okay, so that's the line integral. That's one that we use typically for evaluating circulation, but there can be other things we might look at in fluid mechanics.